In section 6.2, we're going to be looking at a specific type of discrete probability distribution called the binomial probability distribution. So the first thing we need to do is define a binomial probability distribution. So a binomial probability distribution is a discrete probability distribution that describes probabilities for experiments in which there are two mutually exclusive outcomes, referred to as success and failure. So in a binomial probability distribution, there's only two outcomes possible. And generically, we're going to refer to those two outcomes as success or failure. Criteria. An experiment is said to be a binomial experiment if, one, the experiment is performed a fixed number of times. Each repetition of the experiment is called a trial. So for example, the basketball problem that we looked at in the previous section, that was a binomial experiment. So in that binomial experiment, the basketball player is shooting free throws, right? So when the basketball player shoots the free throws, there's two possible outcomes. They make the shot or they miss the shot. Two outcomes, so it's binomial there. Now, the basketball player shot 3 times. They were taking 3 shots. So that was a fixed number of repetitions of the experiment. The experiment was performed 3 times, 3 shots. So when we have a binomial, there's going to be a fixed number of attempts, and each attempt is called a trial. So there's going to be a fixed number of trials. And again, it has to be a fixed number. The trials have to be independent from each other. So the outcome of the first trial cannot affect the probability of the second trial or the third trial. So again, for my basketball player, presumably the second shot, whether they make it or not, is independent of the first shot, and the third shot is independent of the first and second shot. This means that the outcome of one trial will not affect the outcome of the other trials. For each trial, there are 2 mutually exclusive or disjoint outcomes, success or failure. So success, that word has a positive connotation. Failure has a negative connotation. In a binomial experiment, success just means whatever it is that we're talking about occurs, and failure means whatever it is that we're talking about doesn't occur. So success is not necessarily going to be a positive thing. If we're talking about, say, getting in a car accident, success would be getting in a car accident, not a positive thing. So whatever it is we're talking about, if it occurs, it's success. If it doesn't occur, it's failure. So if we're talking about something negative, success is a negative. The probability of success has to be the same for each trial of the experiment. So shooting the shots again, the probability of making the first shot has to be the same as the probability of making the second shot, has to be the same as the probability of making the third shot. It can't change each time. Or like flipping a coin. If I flip a coin, each time it's going to have the same probability of landing on heads or tails. The probability doesn't change between flips. So our discrete probability distribution has to meet these conditions in order to be a binomial experiment. Let the random variable x be the number of successes in n trials of a binomial experiment. Then x is called a binomial random variable. Now, what in the world am I talking about right there? So again, we're going to perform our binomial experiment a fixed number of times. So like shooting 3 free throws. When I shoot 3 free throws, what I'm really going to be looking at is the probability of making 0 or 1 or 2 or all 3. So x is going to represent the number of successes. So when I repeat the experiment 3 times, 3 shots, I can either have 0 successes, one success, two successes, or all three successes. That's going to be my random variable, the number of successes. Now, if I shoot, instead of 3 free throws, if I'm shooting 10 free throws, then I have more possibilities. I could have 0 successes, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10 successes. So what X can be is going to depend on how many trials we have. Notation that we're going to use. N is going to represent the number of trials that we have in our experiment. P, lowercase p, is going to denote the probability of success for each trial. So if I'm, say, an 80% free throw shooter, and I'm going to shoot 3 shots, then the probability of making the first shot is 80%. The probability of making the second shot is 80%. The probability of making the third shot is 80% if I'm an 80% free throw shooter. So my probability of success for each shot stays the same, and that's going to be denoted by P. The probability of failure is then going to be 1 minus P. So if I'm an 80% free throw shooter, there's an 80% chance I'll make the shot, which means there's a 20% chance I'll miss the shot. So 1 minus P is the probability of failure. Again, success and failure are complements. Let X denote the number of successes in N independent trials of the experiment. So X, the number of successes, is going to be something between 0 and N, whatever N is. So it can range from 0 to the number of trials. So this is kind of a trickier question than I intended for it to be. But in this example, I wanted you to determine whether the following scenarios represent a binomial experiment. And if they don't, explain why not. I guess we could explain why also. So I've given you 5 different scenarios, and my question is, would this be a binomial experiment? So a random sample of 30 used cars is obtained, and their mileages are recorded. Would this be a binomial experiment? I randomly select 30 used cars. So I select the first used car and I record its mileage. I select the second used car, I record its mileage, and so on. Would that be binomial? Well, if you think about binomial, there has to be 2 outcomes, success or failure. In this scenario, do we have 2 outcomes, success or failure? We do have a fixed number of trials. We're going to randomly select 30 cars. But in this particular case, we have no definition of success or failure, for example. So I would say no, this is not binomial. Really, there's a couple of reasons. One, the mileages that are recorded, they could be anything. It's not just 2 possible outcomes. This is actually continuous data instead of discrete data. So the mileages on the cars are continuous, not discrete. So I think that's what I'm going to say. This distribution is continuous, not discrete. And again, we don't really have 2 outcomes here. We don't have success or failure in this scenario, so that could be another acceptable reason. Now, could I convert this so that it is binomial? If I were to define, say, success as the car has less than 100,000 miles on it, so then failure would mean that the car has 100,000 miles or more on it. So if I had written a random sample of 30 used cars is obtained and their mileages are recorded to determine if it's less than 100,000 miles or something like that. So now success is less than 100,000 miles, failure's 100,000 or more. So each time I randomly pick a car, I either have success or I have failure. Now I would need to know what the probability of success is in order to be able to do anything with it, but that would make it binomial. How about B? A recent study found that 17% of Americans approve of the job Congress is doing. Suppose a random sample of 20 Americans is asked whether they approve or disapprove of the job Congress is doing. Is that binomial? Yes. In this particular case, there's two outcomes. The individual either approves, presumably that's success, or they don't approve, presumably that's failure. We're choosing 20 Americans, so we have a fixed number of trials, and the probability of success each time is 17%. So this is binomial. How about C? A pair of dice is rolled 5 times. The number of 7s is recorded. Is that binomial? Yes. We have a fixed number of trials. We're going to roll 5 times, and we're going to see how many 7s we get. So if we get a 7, that's success. If we don't get a 7, that's failure. And so out of 5 rolls, I could have 0, 1, 2, 3, 4, or 5 successes. That would be binomial. A basketball player who makes 76% of her free throws is asked to shoot free throws until she misses. The number of free throw attempts is counted. Is that binomial? No, this is not binomial. We don't have a fixed number of trials. So it's not like the deal where we shoot 3 and we count how many we make. We're shooting until we miss. So she could shoot 100 times before she misses, or she could shoot 5 times before she misses, or she could miss the first shot. So we don't have a fixed number of trials. So for that reason, this is not binomial. So there is not a fixed number of trials. Now, other than that, I mean, you do have success or failure. You make it or you miss it. And she is a 76% free throw shooter. So each time she shoots, she has a 76% chance of making it and a 24% chance of missing it. So in that part of it meets the conditions, but the fact that it's not a fixed number of trials is why it is not binomial. How about E? 5 cards are drawn from a standard 52 card deck without replacement. The number of diamonds is recorded. Is that binomial? No, this is not binomial. Think about the probabilities. I'm drawing the 5 cards without replacement. So when I draw the first card, what's the probability it'll be a diamond? 13 out of 52. So now what's the probability the second card will be a diamond? So it would be 12 out of 51 if the first one was a diamond. If the first one's not a diamond, then it would be 13 out of 51, right? So what we don't have in this case, we don't have independence. The trials aren't independent from each other. And so that means it's not binomial. So it's not binomial because the trials are not independent. And the reason why they're not independent is because we're not replacing the cards. Now, if I drew a card, put it back in the deck, and shuffled, and then redrew the card and put it back in the deck and so on, then now that would be binomial if I did that 5 times. So if I drew 5 cards with replacement in between the drawings, that would be binomial.